Okay, take a look at this variation of the problem. In this case, I don't tell you which degree polynomial I'm going to use. In fact, I tell you the error that I want. I want it to be good up to 3 decimal spots. So I want it to be within 1,000. And I give you the interval. Usually you have 3 items here. You have the unknown n, you have the error here, and you have the interval. Usually if 2 of these 3 are given to you, you can figure out the third one by plugging them into the formula. That's how all these problems go. So in the previous one, you were given n was equal to 4, and you're given an interval, and we had to find the error. The error was 0.7 something. In this case, we're given these two, and we have to find n. No problem. We still go with the standard formula. We plug things in, and we get that. We know that this guy is either sine z or cosine z because of the function f of x was equal to sine x. So therefore, when you take derivatives and more derivatives and more derivatives, it doesn't matter which derivative you're at. You are either at sine or cosine or negative of each one of them. In absolute value, that's never worse than 1, so you can omit it. There's a 1 here that's being multiplied and controlling this inequality in a precise way. And I know that x comes from that interval, so I can substitute my x in there, and that gives me this bound. Still, the thing I don't know is n. But I do know that I want this to be less than 0.001. That's what I do know. So the algebra may be kind of hard here to figure out to solve for n, but another attempt here, because these numbers grow fast so rapidly, the bottom grows faster rapidly, you could just try trial and error. If you plugged in 4 here, as we did earlier in the previous example, you would get that. That's plugging n is equal to 4. Plug it into there, plug it into there, put it in a calculator, and you get that. You say, well, that's not less than 1,000th. Why don't we try 5? And so we do. And if you try 5, you would get, if you plugged in 5 in here and 5 in there, you would get that that's less than 0.02. Well, that's not less than 1,000. So then you try 6, and if you try 6, you'd get something like this by plugging in 6 here and 6 there. And if you plug in 7, you get that that's in fact smaller than 0.0009. So therefore, we've got ourselves an error that's smaller than 0.0001. And so 7 would be enough. 7 would be enough to answer the question here. Which n, think about it, which n would give you that the difference between sine and the nth polynomial is less than 1,000? We answered it, n is equal to 7. So in other words, all I have to do is do this. Sine of x is approximately x minus x to the 3 over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. And there, in this range between pi over 2 and negative pi over 2, this is a really, really, really good approximation of sine. How good? It's within 1,000. That's how good. Nice, huh? Give it up for Mr. Lagrange.